Okay, I think we are ready to start. Okay, so today we will first look at a paper that was published several months ago at Micro 2021. And we will cover one more paper that is quite relevant to this topic, and it was published the year before. Okay, so let's start with this first one, right? So the title of this paper is Uncovering in-DRAM RowHammer Protection Mechanisms, a New Methodology, Custom RowHammer Patterns and Implications. And for short here, we call the mechanism UTR, which is basically an acronym that we made up from uncovering the TRR mechanisms. And yeah, okay, I will explain what is TRR here in the upcoming slides. So the RowHammer vulnerability leads to critical reliability and security issues, as we discussed previously, and target row refresh, and which TRR is the acronym for, is a set of obscure, undocumented, and proprietary RowHammer mitigation techniques. So basically, there are three major DRAM manufacturers, right? Or we can count some more maybe, but all of them implement some sort of RowHammer protection mechanisms inside their DRAM chips, and they are not documented, or their implementation details are not exposed in any other way. But I guess they all call them TRR mechanisms. Okay, at least this is what we will call these RowHammer protection, in-DRAM RowHammer protection mechanisms in this presentation. Okay, so what we ask ourselves is, are these TRR mechanisms fully secure, and how can we validate their security guarantees? So manufacturers marketed their DRAM chips as RowHammer free back in, I guess, 2016 or 17, but they did not provide any security proofs, right? So, and this is why we ask these questions ourselves. And to understand how TRR mechanisms operate, we developed a methodology that we call UTR. It is a methodology that leverages data retention failures in order to uncover the inner workings of TRR and study security. And I will explain more how we can use these data retention failures as a sort of a side channel to figure out the inner workings of these TRR mechanisms. So here's a high-level operation. First, we profile the retention time of a row R. So it is just like an arbitrary row in a DRAM bank. And then in the second step, we find when TRR refreshes this row R in order to understand the TRR mechanism, right? So we basically continue to monitor when this row fails or it doesn't fail, and then try to make some observations based on those patterns. So here's a summary of our analysis. So we looked into 15 different modules, DDR4 modules from each of the three major vendors. So here they are anonymized as vendors A, B, C. So we use this methodology to understand how the TRR mechanisms in these 15 different modules from each vendor operate, and they'll craft new RowHammer access patterns that circumvent these protection mechanisms. And here are the results, right? So all 45 modules that we test are vulnerable to certain access patterns. And our access patterns were able to induce 99.9, we're able to use bit flips in 99.9% of the rows in a DRAM bank, right? So yeah, basically we were able to cause a bit flip in almost any row in a DRAM bank. And we observed that these access patterns lead to up to 7 RowHammer bit flips. And this is important because this is making ECC ineffective, which is usually designed to correct or detect to correct one bit error or one symbol, or detect two bit errors or two symbols. Okay, basically being able to cause so many bit flips is making ECC ineffective, and yeah, ECC basically cannot correct or detect so many errors. Okay, and we believe UTR can enable more secure RowHammer solutions going forward. So here's the outline of the talk. I will start with DRAM operation basics. So I will try to cover these relatively quickly because we covered those in the previous meetings too. So here again, you see the, I think this is the same slide that I covered in the previous slides. So here's a DRAM bank, a memory controller, and a CPU. And the memory controller communicates with the DRAM module over the memory bus, right? And all chips here operate in lockstep in parallel. This is the DRAM cell, the sense amplifier, and the DRAM row, just like to remind you what the DRAM looks like. And when we access the DRAM, the memory controller issues 3 commands mainly, right? So the activate command to open the target row that we would like to read to, that we want to read from or write to. And then we perform the read and write operations on the sense amplifiers. And finally, the memory controller precharges the open row in order to be able to activate another row from the same bank. Okay, and each DRAM cell encodes information in leaky capacitors. This is important because basically a DRAM cell leaks the charge over time. And if it is not refreshed or the charge in the capacitor is not replenished periodically, it cannot basically retain the data correctly for a long time. And yeah, stored data is corrupted if too much charge leaks. Or we can say the capacitor voltage degrades too much. Okay, and so here you can again see like what a single DRAM cell is composed of. So it just uses a single access transistor and a single capacitor, and multiple cells are connected via word lines and bit lines. Okay, so yeah, we said that DRAM cells need to be periodically refreshed, and here's what refresh looks like. When a DRAM cell is not refreshed for some time, it gradually leaks its charge. And if the charge drops below this threshold here, denoted as V min, right? So like this line over here, it basically cannot store the data correctly, right? The data cannot be read correctly. But like above this threshold, we say that the data is stored correctly and it can be read or written without any bit flips. And so basically, in the worst case, this is the point where the memory controller or the DRAM chip has to refresh this DRAM cell in order to prevent too much charge leakage. And yeah, periodic refresh operations preserve the stored data. And basically, these periodic refresh operations happen at fixed intervals as depicted here. Okay. And yeah, moving on to the RowHammer and target row refresh. This is also like some sort of like a background slide that we will cover. So like very quickly again, let me define what is the RowHammer problem. So here, let's assume that we continuously open and close row 2, right? So like we perform this operation many times. So what happens is these like many repeated activations within a short time frame cause electromagnetic interference, which accelerates the charge leakage in the cells of the nearby rows. Here, in this example, those are rows 1 and rows 1 and 3. And we call those victim rows, right? So like the row that we repeatedly activate and precharge is called the aggressor row, and the row 1 and 3 here are the victim rows. And this operation of repeatedly activating and precharging the row basically can cause RowHammer bit flips in nearby cells. Okay, and it may even cause bit flips in rows that are a bit further away than the aggressor row, but yeah, it is much more difficult, let's say. Yeah, and we call those rows that are affected by this hammering action as victim rows, and the other row is aggressor, as I already said. Okay, let me also talk briefly about target row refresh. So DRAM vendors equip their DRAM chips with proprietary mitigation mechanism known as target row refresh, or TRR for short. So what is the TRR mechanism? We don't exactly know, but the key idea of TRR is to refresh nearby rows upon detecting an aggressor row. But we don't know details such as what is an aggressor row and when exactly these nearby row refreshes happen. And there are like, when you start like digging deeper, you find out like different questions that are not answered. And we will briefly discuss those in this presentation. So yeah, if you illustrate how TRR operates, it is like doing something like I will show in this animation. So again, we have the 5 rows from the previous slide, and we have a TRR mechanism. So like when we repeatedly activate row 2, the TRR mechanism eventually detects this row 2 as an aggressor row. Okay, so this is assuming like a TRR mechanism that operates correctly and is able to detect the row that we hammer. So then upon detecting this row 2 as an aggressor row, the TRR mechanism refreshes the neighbor rows, which are row 1 and row 3. And it does so during the time allocated for performing regular refreshes normally, right? So, and some of the refresh commands, like during the execution of, during servicing some of the refresh commands, the TRR mechanism squeezes in some additional refresh operations to the neighbor rows. And we could call those TRR-induced refresh operations. So like these are additional refresh operations performed on top of regular refreshes that regularly refresh all rows within DRAM with fixed time intervals. Okay, so basically here the idea is, the thing is that the TRR mechanism is using these refresh operations in order to perform the extra refreshes in a way hidden from the memory controller, right? So like the memory controller is not able to tell whether a neighbor row refresh happened or not, because like the additional refreshes are squeezed in within the time interval normally allocated for regular refreshes. Okay, so what is the problem with TRR? It is obscure, undocumented, and proprietary. And why this is a problem really? It is because we cannot easily study the security properties of TRR, and the DRAM vendors do not provide these security guarantees. Okay, so the goal, our goal in the study is to study in-DRAM TRR mechanisms to understand how they operate, assess their security, and secure DRAM completely against RowHammer. Okay, let's move on to the Utr methodology. This is a new methodology to uncover the inner workings of TRR. And the key idea is to use data retention failures as a type channel to detect when a row is refreshed by TRR. So I will do my best to try to explain what we do here exactly. So the UTR mechanism is composed of 2 main components, which we named as row scout, RS, and TRR analyzer. So the purpose of row scout is to find a set of DRAM rows that meet certain requirements as needed by TRR analyzer and identifies the data retention times of these rows. So let me try to explain with this diagram what it does, right? So like we have the row scout here in the middle. The user, or the person that we will, the person that will perform these experiments will analyze the TRR mechanisms, define some sort of requirements for a row scout, right? And these requirements can be the row group layout, row group count, bank, and range. So like bank and range are simple to explain. Bank is basically in which row, in which bank to search for rows, and range is in which row range within that range, within that bank to search for, right? So like range can be defined, for example, as from like row address 0 to row address 100, or row address 0 to 1000, or like it could be like in any arbitrary range. Okay, but what are row group layout and row group count? I think I will. I have like a some animation here that we will discuss those later. Okay, so it will be easier to explain that way. But basically, like these are some other constraints related to the location of the rows to search for, and these rows should have similar retention times, if not exactly the same. So let's say they should have similar retention times within a specific margin. I think that's a better definition. Okay, and the output of this row scout mechanism is basically the list of these retention profile rows. So it looks something like the row address and its retention time. This is the output basically. And then the second component here, analyzer uses these RS provided rows, right? The rows provided by the row scout to distinguish between TR induced and regular refreshes, and helps us to build an understanding of the underlying TRR mechanism. So this is just an overview. I will go into more details. But here again, the user specifies experiment configuration, and the user specifies stuff like the aggressor row address, right? Where within the DRAM or in which locations relative to the rows here provided by the row scout, these aggressor rows will be located. And whether there's a need for dummy rows, I will explain the use of these dummy rows, and stuff like how many times these aggressor and dummy rows should be hammered and in which order. These are all need to be specified by the user depending on what kind of experiment the user wants to do. And we basically, to discover the operation of the TRR mechanism, we use this TRR analyzer to basically look into many configurations, right? So like we did a sensitivity study on all of these parameters that you see here in order to like get some observations that will help us build a complete understanding of the TRR mechanisms. And the result of this is basically some sort of like an output that indicates when these retention profile rows are refreshed by a TRR-induced refresh command or by the TRR mechanisms, let's say. And the user, again, uses this output to analyze or analyzes this output to develop some understanding about the operation of the TRR mechanism. Okay, assuming this is all clear, so let's move on to the row scout mechanism and look at it into more detail, in more detail. So the goal is, again, as I said, to identify a list of useful DRAM rows and to profile their retention times. Row scout must find rows with consistent retention times to correctly infer whether a row has been refreshed or not. So here, by consistent, we mean the retention time of a row should not change over time. And it can change due to effects such as VRT, which I believe, again, discussed in the previous meetings. The second requirement is that a row scout should be able to find multiple rows located at certain configurable distances, which is specified with the row group layout here. And these rows located at certain configurable distances should have same or similar retention time within a specific margin. Yeah, and then this is required because we would like to understand whether TRR can refresh multiple rows at the same time. Okay, so let's look at how row scout operates in more detail. So I will have a flow diagram here in this slide. So first, row scout finds DRAM rows with retention time T. Initially, we start with some very low retention time. So let's say 64, well, at 64 milliseconds, ideally, we should not observe any bit flips. So let's start with something small, but not too close to 64 milliseconds. Let's say 100 milliseconds, right? So at 100 milliseconds, theoretically, there can be retention failures, at least at very high temperatures. Okay, so at the first step, we find all DRAM rows within a DRAM bank that fail after the retention time of T. And the output of this first step is basically these row addresses. Yeah, and how do we do this? How do we find the retention the rows that fail after the retention time T? It is quite simple. We write some known data, such as all ones or all zeros, into the rows. We just wait for the time interval T without refreshing these rows and check for retention failures. If there are any bit flips, we mark these rows as rows that cannot retain their data correctly for time interval T. The second step is combining rows to match the row group layout provided by the user. So here, the row group layout can look something like this, right? So this is just an example. So in this example, we have 3 victim rows or 3 rows that we would like to find such that they are 1 row apart, right? So like in between them, there are 1 other rows that we don't care about. We don't care what is their retention times, right? But we care about these 3 rows, and they should have very similar retention times. Okay, so basically these are one row apart. Let's say, for example, this first V is at row address 1, this is row address 3, this is row address 5. And we can use these rows in the middle potentially as aggressor rows when we do the analysis in the using the TRR analyzer. Okay, and the output of this second step is basically candidate row groups. So we call these the rows that will match this pattern or some other pattern. So it could be just like V space V, right? So like without these like last two symbols, or it could be anything really. Okay, and then in the second step, we combine those into row groups, and output is the candidate row groups. Why are these candidate? It is because we don't know if these are useful, right? So we don't know if these rows will have this retention time consistently over a long time period. And okay, so like first thing we check is if these candidate row groups, the number of candidate row groups is sufficient, right? So the user might be looking for multiple of these row groups, right? So row groups in different locations within a bank, but let's say the user wants 5 of these. And this again can be useful in the analysis in the later step when the user wants to look at which row the TRR mechanism detects first as an aggressor row, and when so basically in which order the aggressor rows are detected. Okay, if there are not enough candidates, what we do is we increase T and try to find more rows. This time, rows that will fail at higher retention times. So instead of like 100 that we initially started with, we will look for rows that fail after 200 nanoseconds, maybe. Oh, sorry, 200 milliseconds. Yeah, and the reason we start with very small retention times is we can also start with 1 second or 10 seconds. It will work correctly. But the reason why we start with small retention times is to basically make this process faster, right? So like if you start with 10 seconds for each profile, like to profile each row, we will need to wait 10 seconds without doing anything. And basically the experiment will take much longer compared to working with small retention times. And this is why we gradually increase the retention time and try to find rows that have small retention times. Okay, but if we have enough candidates here, what we do is in step 4, we verify the retention time consistency. And to do this, we basically repeatedly test the retention times of these candidate rows and make sure that they always fail after time interval T. And we repeat this for 100 or 1,000 iterations, right? So like in all of these 100 iterations, the row should always fail. Otherwise, we discard it from the candidate row group set. And if we have enough row groups that pass this verification step, we are done. And if that's not the case, we again return to step 1 by increasing T, same as in step 3. And we try to basically find more rows that fail at certain retention times. But if we have enough row groups, we are done. The row scout outputs the retention profile rows file, which again, as I said, contains the like addresses of these row groups and their retention times. Okay, moving on to the second component, TRR analyzer. So the goal of this second component is to determine when TRR refreshes a victim row. And the high-level operation is to run a certain DRAM access pattern or a RowHammer attack potentially, and monitor the retention failures in these profiled rows that we have obtained using the row scout. Okay, and finally, we develop understanding of the underlying TRR operation using the output of this of the TRR analyzer. I will try to.
Excuse me. So we are attacking the rows that are next to what row scout selected, not the ones that row scout selected, but right next to it, right? So we can detect if it got refreshed or not.
Exactly, yes. This is the typical experiment.
Okay, thanks.
Yeah. But I guess we will discuss that in a bit more detail in the following slides. So here, let me try to explain how TRR analyzer operates using a timing diagram. So initially, at time 0, let's say, what we do is we initialize data in victim rows and aggressor rows. So the user specifies which will be the aggressor rows. And the victim rows are those that are provided in the this list of retention profiles rows. And here we have some acronyms, right? So V stands for victim row or arrest provided row here. A is for aggressor row and D is for dummy row. Okay, so initially we just write some known data into the victim rows and aggressor rows. And here, for example, let's assume that we use this row group. So like this is the row group that is in the retention profile rows file here. And we specify aggressor rows between these victim rows. So we can specify only one aggressor row and hammer only this row as illustrated here. And this aggressor row will mostly affect the 2 victim rows that are closest to this aggressor row. But we can also specify an aggressor row here. And in that case, these 2 aggressor rows will hammer all the victim rows, but they will have the highest effect on the middle victim row here, which is sandwiched between the 2 aggressor rows. Okay, so like the user is free to specify aggressor rows anywhere within the proximity of these victim rows. So we can also have aggressor rows here and here, but those will affect only this victim row and this victim row. Okay, and in the next step, so I won't explain this too much, but this is basically an optional step that the user can perform in order to reset TRR's internal state. And why this is useful? So assume that we run a previous experiment that potentially changed the RowHammer state, right? So like due to a previous experiment, the TRR mechanism currently have some rows registered as potential aggressor rows. So we may not want to, or the user may not want to, these like previous experiments to interfere with the current experiment. And this reset step is basically issuing a lot of refresh commands and a lot of dummy row activations in order to clear that previous state with some like dummy information. Okay. And another purpose of this step is to prevent these victim rows and aggressor rows that we activate in order to initialize them from being detected as aggressor rows. So we'll activate each row only once here, but depending on how the TRR mechanism detects aggressor rows, it is still possible that these victim rows and aggressor rows, or some of them, will be detected as aggressor rows, even if we activate them only once, right? But here in this reset step, we can just activate some other rows, some other dummy rows many times in order to simply make the TRR mechanism forget about these rows that we activated here. Okay, and then after initializing these V's and A's, if we wait for time interval T, which is the retention time of these victim rows, and later we read the data, what we expect is to have some bit flips, at least one bit flip in each victim row, right? So like this is what we expect to happen if we don't do anything here in between. Yeah, so expecting retention failures in V. However, if we do some, if we issue some refresh operations here, some refresh commands here, there are 2 possibilities, right? So first, the regular refresh commands may target these victim rows just like by chance. So it is just like victim rows turn to get refreshed, right? So like this has nothing to do with TRR. Yeah, okay, so they can be refreshed due to regular refresh. And second, they can be refreshed due to TRR mechanism. Right? So like, but normally if you do the reset operation here, we do not expect these victim rows to be refreshed by the TRR mechanism, assuming that this reset stage or the reset step is done properly. Okay, and so basically if these refreshes target and refresh one of these victim rows, then in that case, the victim rows will be refreshed after after half of t, basically, and we expect no retention failures to happen within this half t interval, and it is because we know that the these victim rows will fail after time interval t, but they should not fail after time interval of half t. Okay, and same here, right? So like these rows will be refreshed here in the middle, and they will have, again, the same t divided by t interval to leak their data, and we don't expect to see failures in that case. So this is basically how we figure out whether these victim rows have been refreshed, either due to regular refreshes or TRR refreshes. Okay, and here, before the refresh operations, the user can optionally perform hammers, right, which are just activate and pre-catch commands to the aggressor rows and optionally to the dummy rows. So the dummy and aggressor rows are the same thing. So they are just like some row addresses that we hammer, but we illustrate them separately here because the aggressor rows are those that are close to the victim rows, but dummy rows are usually rows that we use in order to trick the TRR mechanism to refresh to like detect dummy rows as aggressor rows. But these dummy rows are actually somewhere further away in the bank, right? So their neighbor rows are not these V's that we actually try to hammer and cause bit flips. So like this is the difference between the aggressor rows and the dummy rows. And basically, so here we can easily observe when we hammer certain aggressor row a lot, we expect the TRR mechanism to normally detect this aggressor row as an aggressor row and refresh its neighbors when we issue those refreshes over here. Okay, and basically by doing these kind of experiments with different configurations, with different number of hammers, different number of aggressors, hammering these aggressors in different order, using dummy rows, we try to understand how this TRR mechanism operates, right? So like what is the policy to detect an aggressor row? Does it detect an aggressor row when it is hammered by, let's say, at least 10 times or 100 times? Or does it otherwise do not detect the row as an aggressor row? So we try to answer this kind of questions by repeatedly doing many experiments with different configurations. Okay, and yeah, so as a takeaway, TRR analyzer helps us to understand how TRR operates based on when the retention profile rows are refreshed by TRR. Okay, so this was about the components of the UTR methodology, and I will now present the observations that we made using UTR. And yeah, we analyzed 45 different modules, as I mentioned in the summary. So we implemented UTR using SoftMC, which we discussed a lot in the previous two meetings. We used the this FPGA board that you see here with DDR4 sodium support. So here you can see the FPGA board. You can see the DRAM module. Well, you cannot actually see the DRAM module because of this clamp over here. And this clamp is basically holding two silicone rubber heaters that are stick to the DRAM module. And using the temperature controller here and those heaters, we heat up the DRAM chips to certain temperature point, and we keep them at that temperature point during the experiments. And this is because most experiments are sensitive to temperature. And in order to get meaningful results, we have to operate the DRAM always at a certain temperature. Otherwise, the results will be different across experiments. Okay, so SoftMC provides fine-grained control over DRAM commands, timing parameters, and temperature. We analyzed 45 DDR4 DRAM modules from 3 vendors named as vendor A, B, and C. And here is the table, which you can also see in the paper. And here we provide a summary of our observations. So some of the modules in the set of 45 modules are like the same modules in the sense that they are from the same batch, right? So they have like similar properties in terms of like organization and manufacturing date, chip density, and etc. So like this first part over here, these first columns are related to the organization of the DRAM chips. Here, this is like the HC first value that we found using experiments with SoftMC. And HC first it stands for hammer count to cause 1 bit flip. Right? So basically, this is the minimum hammer count needed to cause a bit flip in any row in this DRAM chip. So as you can see, some DRAM modules have very low HC first values. So I think the smallest here is like 11K, 11,000, but some modules are much more tolerant against like these hammers. And then you can see here, for example, this module over here has HC first value of like roughly 160K. And here are some other observations that we made related to the operation of the TRR mechanism and some results on these two last columns. So I won't go into detail here, but we may come back to this table later after we explain our observations in a bit more detail. But this is basically a summary table that can be used as a reference. Okay, so let's start with the key observations of the TRR mechanism of vendor A. So we observed that there are two types of refresh commands performed internally, or two types of refresh operations performed internally. Regular refresh and two TRR capable refresh commands here that we name as TRF1 and TRF2. So those are the three operations that happen when the memory controller issues a single refresh command. Right? So it is either regular refresh, it is either TRF1 or either TRF2. Okay, what is the difference? So we find that 8 consecutive refresh commands that the memory controller issues perform regular refresh operations. But the 9th refresh command in the sequence is performing TRF1. And similarly, the next 8 refresh commands are again regular refreshes, and the 9th refresh is this time TRF2. And this continues in this loop, right? So like 8 refresh commands followed by TRF1, 8 refresh commands followed by TRF2, and then this repeats over time. Okay, so I'll explain what is the difference between TRF1 and TRF2. So the observation is that the TRR mechanism of this vendor A tracks potentially aggressor rows using some sort of a counter table. We suspect this counter table to have 16 entries, and the counter table looks something like this. Each entry has an entry that consists of a row ID. So this is the row ID of the potential aggressor row, and some sort of like a counter that indicates how many times this row has been activated. So TRF1 refreshes the victims of the row ID with the largest counter value in this table, right? So like when it is turned to perform TRF1, the TRR mechanism looks up this table and finds the row ID that corresponds to the counter value, the highest counter value, and refreshes the neighbors of that row. So this is TRF1. And TRF2 refreshes the victims of row ID that TRF2 pointer refers to or points to. So basically here we suspect that they implement an additional like a counter that basically cycles through these entries each time a TRF2 is executed, right? So like, let's say during the execution of this TRF2 command, this second entry that you see here in the table will be, or the neighbors of the second entry will be refreshed. And this TRF2 pointer will advance to the next entry, right? And at each TRF2 command, it will refresh the next entry or the neighbors that correspond to the row ID in the entry and advance to the next entry. And then this happens in circular manner, right? So like after coming to the end of the table, it returns to the first entry. And this is how TRF2 operates. Okay, so let's talk about how we can circumvent this TRR mechanism, knowing these two observations, or not two observations, but these observations regarding the TRF2 and TRF1 operation. So our approach is to ensure that an aggressor row is discarded from the counter table prior to a refresh command, right? So here is what the access patterns look like. So after a refresh command, we can activate the actual aggressor rows, A1 and A2. Here we assume a double-sided RowHammer attack. We can activate these two rows n times, and n is configurable depending on like some other parameters, right? And afterwards, we have to hammer 16 different dummy rows, and then we need to hammer those n+1 times at least in order to evict these A1 and A2 from the counter table. And when these activations are followed by the next refresh command, and these refresh commands happen under like normal, like real system operation, these happen at certain fixed time intervals, right? Let's say every 7.8 microseconds at the default refresh rate. And here we basically try to ensure that these two rows, A1 and A2, will not be in the counter table, although we hammered them for some number, right? So like, and we hammered them n times each. And yeah, this is the idea basically to circumvent the mechanism, to circumvent this TRR mechanism. This RowHammer access patterns require synchronizing accesses with refresh commands, right? So like here we need to know when the refresh happened. And so like we can immediately follow that refresh command with the actual hammers and then follow them with dummy row activations. So this is not a huge problem, even with a real system, although this is very easy to do with SoftMC. In a real system, it is very easy to figure out when the memory controller issues refresh commands, because when the memory controller performs a refresh, the latency of the memory access slightly increases. And this can be basically observed with a timing side channel, and prior work shows how this can be done using like even from the browser without any root privileges. And yeah, basically circumventing vendor A's TRR by discarding the actual aggressor rows from the counter table is possible. Okay, and this is the access pattern that we basically develop, and this is how we attack the modules of vendor A. Okay, moving on to vendor B. So yeah, so here we observe that there are only two different refresh operations, just regular refresh and one TRR capable refresh command. And the schedule of these TRFs are like this, right? So instead of like following 8 regular refresh commands with one TRF, here for vendor B, we observe that every like after 3 consecutive regular refreshes, a TRF happens, and then this repeats like this. And the first observation we make here is that TRR probabilistically samples the address of an activated row. And the second observation is that newly sampled row overrides the previously sampled one. So let me try to explain this in a little bit more detail. So when the memory controller sends an activate command, let's say activate row 101, the TRR mechanism with some low probability samples this row and registers it as a potential aggressor row. So even if we activate that row only once, there's a chance that it will be sampled, right? And the TRR mechanism remains or keeps this row 101 detected as aggressor row until another row is sampled, again with a very low probability. And sampling another row overrides this previously sampled row. Okay, I hope that's clear. And while a row remains sampled, it continuously refreshes that row during all these TRF commands, right? Even if that row is not accessed anymore, it will keep, the TRR mechanism will keep refreshing row 101 during these consecutive TRF commands. Or I should say the neighbors of this aggressor row. Okay, so if I say that refreshes the aggressor row, I really mean the neighbors of the aggressor row. Okay, and so basically the TRF command here refreshes the victims of the last sampled row, if we put it into like one simple sentence. And how do we circumvent this TRR mechanism? It's quite simple. we maximize the number of hammers after hammering the aggressor rows and before the next TRF. So we basically try to here activate as many dummy rows as possible in order to make the TRR mechanism sample a dummy row and override a potentially previously sampled aggressor row. And here's how the access patterns looks like. After a TRF command, we hammer the actual aggressor rows n times, and then we hammer a single dummy row. So single dummy row is sufficient. We don't need 16 dummy rows or more than one dummy row, because like our goal here is to make the TRR mechanism sample this dummy row, right? So like it doesn't matter if you activate multiple dummy rows or just a single dummy row. And yeah, during the next TRF, we hope that A1 or A2 will not be refreshed by the TRR because they will not be rows that are last sampled. And here, basically, there's a trade-off between how many times you can hammer the aggressor rows. We ideally want to hammer them a lot in order to induce RowHammer bit flips. But if we hammer them a lot, we will have limited, lower budgets, lower activation budget to activate the aggressor rows, to activate the dummy rows. And then if we cannot hammer the dummy rows by a large amount, then the TRR mechanism may not sample these rows because sampling happens with low probability. Yeah, and here the total, the activation budget between two TRFs is limited because the time is limited, right? The memory controller will issue refreshes at fixed time intervals. Okay, and circumventing vendor B's TRR by making it replace a sampled aggressor row by sampling a dummy row. So like this is the access pattern that we use to circumvent the TRR mechanism. Okay, and moving on to the last vendor, vendor C. Again, here we have two refresh operations, regular refresh and TRR capable refresh. And the schedule of these TRFs looks like this. So every 17th refresh command is used to perform a TRF. And here the observation is that TRR detects an aggressor row only among the first 2K activation commands issued after a TRF. Right? So like after this TRF command until the next TRF, only the first 2K activation commands are contributing towards the, or basically, let me put it more in a more simple way, only the first 2K activation commands have the chance to be detected as aggressor rows. And all activations you do after the first 2K activations are just ignored by the TRR mechanism. And you can use those activations to hammer aggressor rows. And observation 2 is that rows activated earlier within the 2K activation commands are more likely to be detected by TRR. So we couldn't figure out exactly how the TRR mechanism detects detects an aggressor row. Their mechanisms appear to be slightly more sophisticated compared to the other two vendors. So it is possible that they use some randomness. Because we were not able to observe like a clear pattern in their detection policy. But still, this observation is sufficient to build an access pattern that circumvents the TRR mechanisms. Okay, so our approach is to hammer dummy rows before aggressor rows to maximize the probability of TRR detecting a dummy row. So we said that only the first 2K activations can be detected, right? And this is exactly what we do. So we activate a dummy row n times, and this n is as close as possible to 2K, right? So it could be smaller as well. Most of the times you were able to observe bits with smaller than 2K activation commands, and it is because of the second observation, right? So like as we approach the 2K activation commands, these later activation commands become more and more or less and less likely to be detected by the TRR mechanism. So even if you perform less than 2K activations or 2K dummy row activations, it is possible that these actual aggressor rows will not be detected by the TRR mechanism. Yeah, and this is the access pattern that we use. Yeah, and
one question.
Yeah.
For the table above, for different vendors, did you use a customized RowHammer policy to find out the hammer count, or did you use the same one to find out the hammer count, or did you use the way that's most effective or vulnerable for the vendors?
Yeah, so in that table, actually, HC first, the hammer count is just like the like minimum hammer count without any TRR, without any protection.
Okay, so TRR is not considered.
Yeah. So it is really like an experiment we did to find out like what is the vulnerability level of the DRAM rows without any protection.
And is there like any result? How many hammer count after with the protection?
Yes. I'm almost there.
Okay.
Yeah, and yeah. So here in this in this section of this talk, we will discuss like we will look at the results basically, and yeah, we will see like the bit flip analysis that we did. So we craft new RowHammer access patterns that circumvent TRR of the 3 major DRAM vendors, and we looked at 45 different DRAM modules, as we said. And our new access patterns cause a large number of RowHammer bit flips. And so here, this plot shows. So it is not showing like the exact number of bit flips, but we have that data in the paper for sure. I'm not sure if I included those in this slides. But what this plot is showing is on the x-axis, we have each of the 45 different modules here labeled as A0, B0, and etc. Y-axis represents the percentage of DRAM rows that have at least 1 bit flip. And these are the number of, these are all DRAM rows within a bank. Okay, so, and here we have some observations, right? So the first observation is that all 45 modules we tested are vulnerable to our new RowHammer access patterns. And so like in some modules, we have lower percentages of vulnerable DRAM rows, and this is with TRR, right? So like, just to make it clear, this is with TRR. We observe that, yeah, we are able to induce bit flips in all DRAM modules. The second observation is that in many modules, we were able to cause a bit flip in almost all rows in these modules. Okay, but why are some modules less vulnerable? We find that this is due to 3 reasons. So first, these modules are fundamentally less vulnerable to RowHammer. So if you go back to that table and look at the HC first value, so you will find that these modules highlighted here have relatively higher HC first values. So these are just inherently more tolerant. The second reason is that they use slightly different TRR mechanisms. So we found that some observations do not hold for these modules, and these are these modules from B9 to B12. So they use similar mechanisms, but we suspect that there are like slight differences in the configuration of the TRR mechanisms, that our access patterns do not work as good as in the other modules. But it is possible to analyze these modules further and find out exactly what are the differences and craft RowHammer access patterns that have higher percentage of, that achieve higher percentage of vulnerable rows. But yeah, we were able to see bit flips, and the number of bit flips we see is still huge. Like being able to induce bit flips in like over 30% of the rows is still huge. And we found that some modules have unique row organization. So here we suspect that the vendors do some sort of like an mitigation mechanism in the DRAM circuitry. So it appears that rows are somehow isolated from each other, such that even if you hammer these rows without any TRR protection, without issuing any refresh commands, it is very difficult to cause a RowHammer bit flip. Right? So like mostly the organization looks something like you can cause a bit flip only on one side of a aggressor row. Right? So let's say the row above is the one that is vulnerable, but the row below is not vulnerable, even without any refresh commands that are needed to perform TRR. So this is what we suspect. Okay, but yeah, overall, our access patterns successfully circumvent the TRR implementations of all 3 major DRAM vendors. So let's also talk about the ECC, right? So whether ECC can be used to protect against our access patterns. So this is what a typical ECC DRAM module looks like. So here we have 4 data chips and 1 ECC metadata chip. When we read data from this DRAM module, the 4 DRAM chips return like let's say like the actual like data, and the ECC chip provides some like parity information in order to detect and correct the potential bit flips in the data, right? So like this entire, so we call each of these 16-bit data chunks or 2-byte data chunks as ECC symbols. And this is the 8-byte data word, right? The data that comes from the data chips. And we call this entire 9-byte data chunk as a code word, an ECC code word. And depending on how the ECC policy is implemented, the ECC engine, which usually sits in the memory controller, can correct 1 bit or 1 symbol and can detect 2 bits or 2 symbols. But it cannot correct more than 1 bit. It cannot detect more than 2 bits or 1 and 2 symbols. Okay, and here are some results that show the number of bit flips our access patterns cause in a single 8-byte data chunk. So on the x-axis, we show the data collected from modules from different vendors ABC, and the y-axis is the number of 8-byte data chunks with 1, 2, 3, up to 7 bit flips. So here the observation is that most data chunks, and not that this is in log scale, right? So the y-axis is on log scale. Most of the 8-byte data chunks contain 1 bit flip. Oh, of course, we don't include here data chunks do not have any bit flips, right? So there are such data chunks as well, but here we're interested only at like seeing what is the distribution of like how many bit flips at most our access patterns can cause in a single data chunk. Okay, most of the bit flips, most of the data chunks contain only 1 bit flip, and this can be corrected by ECC. However, we see data chunks with 3 and up to 7 bit flips, and these are bit flips that the typical ECC schemes cannot detect, cannot correct or detect. Of course, it is possible to design stronger ECC schemes, but these come with additional costs. The metadata storage needs to significantly increase, and also like the cost of like encoding and correcting and encoding and decoding the code word also increases. And this is why in DRAM systems, mostly system designers or DRAM vendors use simple ECC schemes that can correct and detect that can correct 1 symbol or 1 bit error and can detect 2 symbols or 2 bit errors. Okay, yeah, and here you can see that we see like up to 7 bit flips in these models from vendor B and C. Yeah, and here are conclusions that conventional DRAM ECC cannot protect against our RowHammer access patterns. We have more observations on the TRR mechanisms of the 3 vendors in the paper. We have detailed description of the crafted RowHammer access patterns. We have Hammer's per aggressor row sensitivity analysis, right? So like here you can find the actual number of bit flips that our access patterns can cause with the presence of the TRR mechanisms. And we have like a lot more observations and results for individual models. So yeah, if you are interested, I definitely suggest you check out the paper. And here's the table again, right? So like here in this table, we actually do show the maximum number of bit flips per row per hammer. So like this is some sort of a metric we developed in order to sort of like show the bit flips in these models in a comparable way. Right? So like, yeah, so for example, here for module B7, we can see that with a single hammer, we cause something like 31 bit flips. So across the entire module, I believe. Yeah, and so here you can compare these like further. And again, so this vulnerable DRAM rows is what we showed in the plot. And here we have some details about the configuration or operation of the TRR mechanism, right? So like this TRR to ref ratio is what I showed in the timelines in the previous slides regarding the schedule of the TRF versus regular refresh operations. Yeah, and here are some more details that we explain in the paper. Okay, so let's conclude. Yeah, so TRR is obscure, undocumented, and proprietary. Manufacturers, for some reason, did not provide security guarantees. And we asked these questions whether the TRR mechanisms are really secure. And we developed UTR. We analyzed many different modules, and we show that it is possible to craft new access patterns that circumvent the TRR mechanisms. And yeah, we were able to cause bit flips in all of these modules. Yeah, and the conclusion is that TRR does not provide security against RowHammer, and we believe UTR can facilitate the development of new RowHammer attacks and more secure RowHammer protection mechanisms going forward. And this is the end of this presentation. And I will move on to the second paper, unless you have some questions. Okay, so I will try to cover this paper more quickly. So the paper is called TRRespass for short, exploiting the many sides of target row refresh. So this was published the year before we published the UTR paper. So I wanted to cover these like in order, not in like, so in reverse chronological order, let's say, because like it made more sense as the UTR paper describes things in more detail. Okay, so TRRespass is the first work to show that TRR protected DRAM chips are vulnerable to RowHammer, and mitigations advertised as secure are actually not secure. And TRRespass introduced many-sided RowHammer attacks. So this is basically a collection of RowHammer access patterns that can bypass the TRR mechanisms, but maybe not as good as the access patterns we later found in the UTR paper. And the idea is to hammer many rows simultaneously in order to sort of like try to overflow the TRR tables that detect the aggressor rows. So here by TRR table, we refer to the counter table that we later uncovered more details about, right? And same for the that sampling-based mechanism of vendor B, right? So like if you hammer many rows at the same time, it can be still likely to bypass the TRR mechanism. And in this paper, we also partially reverse engineered the TRR and the PTR mitigation mechanisms implemented in DRAM chips and memory controllers. So we discussed TRR so far, so you know what is TRR, and PTR is an early mitigation mechanism implemented in the memory controller. So here in PTR, the memory controller is responsible for performing targeted refresh operations in order to protect against RowHammer, as opposed to DRAM itself in in-DRAM TRR. Okay, and TRRespass provides an automatic tool that can effectively create many-sided RowHammer attacks in DDR4 and LPDDR4 chips. So this tool is basically like automatically, so it's like a fuzzing-based approach that searches a certain search space and tries out different access patterns until it finds a pattern that can cause bit flips. Okay, so again, here's a slide of how target row refresh operates. So I will just like skip this because like we already discussed these things, but basically the key idea is to track the activations, right, to the row, to like potential aggressor rows and refresh their neighbors. And in-DRAM TRR is like what we already discussed, and I briefly touched on the PTR, the memory control level mitigation. So here's some nice timeline of different TRR implementations. So back in 2013, first the some like CPU manufacturers or design reported that their memory controllers have support for PTR on DDR3 server systems. And this was the RowHammer protection mechanisms implemented back then. And then in 2014, PTR mechanisms were also included in DDR4 systems. And starting from 2016, manufacturers equipped their DRAM chips with in-DRAM TRR mechanisms. And some manufacturers advertised their DRAM modules as RowHammer free. And the current generation as well is just using in-DRAM TRR. And as far as I know, the memory controller-based mitigation mechanisms are not used anymore. Maybe they can be optional turned on. Maybe they still exist, but I think they are not turned on by default. Okay, our goals in this paper are to reverse engineering in-DRAM TRR to demonstrate how it works. We achieved this goal partially, let's say, in this work, and we uncovered more details in UTR. Another goal is to bypass TRR protection with a novel hammering pattern, which we call many-sided RowHammer. And we show that hammering up to 20 aggressor rows simultaneously bypasses TRR. And another goal is to automatically test memory devices using a tool that we named TRRespass, and it automatically discovers hammering patterns for different modules. So here we have some pictures of the old infrastructures that we used. Maybe it will be good to show these to you. So this is the DDR3 infrastructure we used in 2014. Yeah, so like this here in this infrastructure, we use like an enclosure with heaters, and we here basically try to heat the air inside the enclosure. Now we switch to using rubber heaters because it's more efficient, and we can keep the DRAM modules at a certain temperature with a higher accuracy. But yeah, this is how the infrastructure looked back then. And again, here we have the FPGAs, we have the heater marked, the host machine, and the temperature controller. And this is another picture that looks, again, similar to the previous one, but here we have only one setup. The same components. Again, we have a heat chamber here. And I guess in this slide, I again wanted to mention the SoftMC. Here we, for this work as well, we use SoftMC with like initial analysis of the DRAM modules, try to understand the TRR mechanism. But we also did, executed these many-sided RowHammer access patterns on real systems, like on desktop machines and also mobile devices like smartphones. And we were able to see bit flips. Okay, yeah, so here's again reference to SoftMC. So here what our hypothesis was about the operation of in-DRAM TRR mechanisms in the TRRespass paper. So we suspected that it is composed of two components, sampler and inhibitor. So sampler is basically the aggressor row detection logic, right? So like how this can be designed. And here are three high-level design options, right? So it could be frequency-based implementation such that every nth row activation is sampled as a potential aggressor row. It could be time-based, like the first n row activations are counted or are detected directly as aggressor rows, or some like random approach that depends on a coin flip, right? So like the implementation of vendor B, where a row activation has a small probability of being sampled. So regardless, the sampler has a limited size. So this is what we suspected and can be exploited in some way, can be bypassed in some way. Okay, and the second component, the inhibitor, prevents bit flips by refreshing victim rows. And the latency of performing these victim row refreshes is squeezed into the select time available in TRFC, as we already discussed it in the previous presentation. Okay, so like the latency-wise, this operation is hidden from the memory controller and happens internally within the DRAM. And here's, we have a slide where we discuss how big can be the sampler. And we find that it has like limited size. We discussed in the paper, like what exact size we suspect it to be based on our experiments. So I won't like spend too much time on this because like we already covered these observations. And here we have like some heat map to present the results. So I think the font, the text is not perfectly well visible, but I hope you can read it. Okay, so what we show in this heat map is, so I will like show the rest as well, right? So on the x-axis, we have the number of aggressor rows. So we sweep the number of aggressor rows that we hammer simultaneously. So like think of this as like a regular RowHammer access pattern, but we don't do a double-sided RowHammer, but we do like up to 9-sided RowHammer, let's say. So we hammer like 9 different rows in the same bank. And on the y-axis, we have the refreshes per round. And round is basically how many times we repeat a aggressor hammer and refresh cycle, right? So we call this a round. So initially, if you have only one aggressor row, or like 0 aggressor rows or 1 aggressor row, we do not observe any bit flips when we perform at least one refresh operation. And when we don't perform any refresh operations, we are able to observe 2 bit flips. So this is across, I guess, 512 rows within one bank. Okay, so this is not across the entire bank. Okay, only 2 bit flips, right? And then here, basically, with a very small chance, we were somehow able to circumvent the TRR mechanism because there are no refreshes. And these are not retention failures because, like, we complete the aggressor activations and these refreshes in time smaller than the typical refresh period of 64 milliseconds. So, like, without hammers, these rows do not fail. Okay, so like as you can see over here, right? When we do not have any aggressor rows, we don't get any bit flips. Okay, so then when we start increasing the number of aggressor rows, we start seeing more and more bit flips. So here we see almost 3K bit flips when we don't do any refreshes, which makes sense because the TRR protection cannot operate here. But for the first time, we also observe 1 bit flip when we do only 1 refresh per round. So like 1 refresh here is not sufficient to cover all the aggressor rows, all 2 aggressor rows that we hammer. And with some small probability here, we managed to observe 1 bit flip. And here we also like make the observation that the TRR mechanism acts on a refresh command, but we already know that. Okay, and then as we increase the number of aggressor rows, we start seeing that no matter how many refreshes we perform, there are some rows left out unprotected, and hammering them causes bit flips. Right? And as we increase the number of aggressor rows we have, we start causing more and more bit flips. Okay, yeah, and you can study this heat map, this plot on your own more, and yeah, let me know if you have questions, or let me know if you have questions right now. But I guess I explained the key observations here. Okay, and these slides are already available on the course webpage, by the way. So yeah, if you want to look at the slides, feel free to do so. Yeah, and then I guess here's the entire table again, directly taken from the paper. Okay, so we have some observations here. The first observation is that the TRR mitigation acts on every refresh command. So as I said, we already know this. Observation 2 is that the mitigation can sample more than 1 aggressor per refresh interval. And we observe that because of this table here, right? So like it can protect. So you can see that as we increase the number of refreshes, there's a reduction in the number of bit flips. But after 3 refreshes, when we do 4 or more refreshes, we get like roughly like a constant number of bit flips, which means that these additional refreshes do not help anymore, right? So like the unprotected rows remain unprotected. But here, there's a difference between performing 1 refresh and performing 2 refreshes. So potentially the second refresh here is refreshing the neighbors of a second aggressor row. And it is definitely useful. Okay, and the mitigation can refresh only a single victim within a refresh operation. So this is also like observation we can make based on this table over here. And observation 4 is that sweeping the number of refresh operation aggressor rows while hammering reveals the sampler size, right? So like this red line that we draw over here reveals the sampler size. So the sampler cannot track more than 4 cannot track 4 and more aggressor rows. Wait. So it's 3 refreshes. So okay, so here it refreshes 1, the second, the third, and here the fourth. Yeah, 4. It should be 4, right? So like it refreshes the neighbors of 4 aggressor rows. So the sampler size here is 4. Yeah, so here's another plot that shows for vendor C the effect of hammering with the default refresh rate. So like this is normal operation, normal DRAM operation in real system, right? So TRFI is the interval between 2 consecutive refresh commands that the memory controller issues. And in this plot, we see the number of bit flips as a function of the number of aggressor rows. Again, here we do a many-sided RowHammer pattern as in the table. And then here, what I wanted to show you is that we get the most number of bit flips when we use 5 aggressor rows. For some reason, we do not see with 6, but we do see some like smaller number of bit flips as we keep increasing the aggressor rows. So here, the reason we see the most bit flips with 5 aggressor rows is because when we increase the number of aggressor rows, because the total budget for performing activations is limited, we can TRFI here. When we have more aggressor rows, basically the hammers per aggressor rows reduces, right? And then when that reduces, we can hammer each aggressor row less and disturb the neighbors less. And yeah, this is why we think that with 5 aggressor rows, we get the maximum number of bit flips. But as I remember, if I remember correctly, we don't have like an exact explanation why with 6 aggressor rows we do not see any bit flips. But this could be because some like collision that helps the TR mechanism detect the aggressor rows correctly in this case with 6 aggressor rows. But for some reason, yeah, it cannot do so with 5 aggressor rows. So like it could be related to the location of the aggressor rows that we use. So maybe like different access patterns here will be able to cause bit flips with 6 aggressor rows as well, right? So like I mean when the location, when the addresses of these aggressor rows are different. Okay, so and here here we have 3 similar plots for the for like representative modules of the other vendors. So this is a module from vendor C, this is module from vendor A, and then this is a different module from vendor A again. Yeah, and then we have like some like different observations here, but yeah, maybe I will yeah not talk about these right now to save some time. Okay, so and here are the key results. We were able to cause bit flips in 13 out of 42 DDR4 DRAM modules that we tested. And here we were able to cause bit flips in at least 1 module from each of the 3 major manufacturers. And then the we find that 3, 9, 10, and etc. tie that like many-sided attacks are needed to cause bit flips. We also looked at mobile phones, right, to analyze LPDDR4 modules or LPDDR4X modules. So it's just a different standard. And we were able to see bit flips in 5 out of 13 mobile phones that we tested. And these results are just scratching the surface. As we saw in the UTR paper, we were able to do much better using the RowHammer access patterns we crafted, taking advantage of the observations we developed using UTR. Okay, and yeah, the key takeaways are that RowHammer is still an open problem and security by obscurity is likely not a good solution. And yeah, this is the end of this paper. Let me know if you have questions. And otherwise, we are done with the presentations for today. I hope you learned a lot about RowHammer and the current RowHammer mitigation mechanisms implemented in modern DRAM chips, in the DRAM chips that we use in our systems, in the systems that we use daily. And yeah, I hope this was interesting for you to learn. Okay, great. I guess I don't have any. I guess you don't have any questions right now. So So cool, yeah, we will end the session today here, or we will end the live stream at least. And yeah, I guess we will discuss the project. Okay, so there was one question. Does your group focus more on covering flaws in hardware or also mitigation techniques? Yeah, both. Well, you look at the mitigation techniques as well, and we do like this kind of research as well. But today I only presented these two works because they were pretty like related to each other, and I wanted to cover them both. But we also look at the mitigation mechanism. So I think Jirai last week mentioned RowHammer. So it is a RowHammer mitigation technique that our group developed like last year. Okay, great. So let me end the live stream.